Alright, today we're going to look at infinite limits. We're going to determine infinite limits from using limits from the left and right. We're going to use graphs, tables, and logical reasoning. Okay. So today we're going to look at functions that increase or decrease without bound. The first function we're going to look at, straightforward one here, 3 divided by x minus 2. Okay, so I'm going to put that in my calculator. And we're going to look at the table. And we're going to put in 1.5, 1.9, 1.99, 1.999. Okay, so I see I'm going to go from -6 to -30 to -300 to -3000. I know 2 is going to be an error. Then 2.001, 2.01, 2.1, oh, 3,330, and 2.5 would be 6. Okay. So, in terms of how we've talked about limits, in order to have a limit at 2, which is what we're focusing on, this would be our C value and a limit, you have to be approaching the same height. But you can see, as this part of the curve gets closer to 2 and this part of the curve gets closer to 2, this one's going towards negative values very quickly. This one's going towards positive values very quickly. And so they're not going to match up. They're going to continue to get further and further and further apart because one's going down toward -3,000, the other one's going up towards +3,000. So if we were to say, okay, what's the limit as x approaches 2 of f of x, we would say it doesn't exist. Because it doesn't come to the same height or come to the same values, comes to the y value as your x approaches from either side. Okay, but then if we were to change the question to not what's the limit as x approaches 2, but what's the limit as x approaches 2 from the left? Okay, well, from the left, as I get closer to 2, my y values are decreasing very, very quickly. And if I had to predict for 1.9999 would be, it would be -30,000. So it's going to keep decreasing very quickly. Because there's an error at 2, I'm going to assume, based on my data, because that's happening, that you have an asymptote there. So we would say, well, normally we would say, oh, it does not exist because there's an asymptote. But we're going to change our answer to be -infinity. Now, technically, -infinity would be saying the limit doesn't exist because the definition of a limit is a single y value that your graph approaches. This isn't a single y value. However, it does tell me more than DNE does. DNE just means there might be a break in the graph. There could be an asymptote, but I'm not quite sure. This indicates there is an asymptote and what direction the curve is heading as it gets closer to that asymptote. So the limit as x approaches 2 from the left is going to be -infinity. Technically, that means the limit does not exist because it's not a single y value, but this gives me more information about the function. So if we look at the limit as x approaches 2 from the right, it's increasing towards positive y values very quickly, so we're going to say that's positive infinity. All right, so definition of an infinite limit. As x approaches c, f of x increases or decreases without bound. Okay, technically, the limit, as we know it, doesn't exist. In essence, when you say the limit is, let's say, infinity, you are saying the limit does not exist, but you are giving information about the behavior of f of x, because it tells you that at that point your f of x is heading towards positive y values along that asymptote. Okay, so we're going to look at 3 different functions. I'm not going to tell you what this function is, but for each one of these graphs, you're going to have an asymptote along the x-axis. So go ahead and draw that in. And then you're going to have an asymptote through the x value of 3. And each graph is going to look slightly different. Okay, this graph looks like that. There's 2 limits that we're going to find here. The limit as x approaches 3 from the left of this function, we're going to figure out what that is from the graph, and the limit as x approaches 3 from the right of this function. Okay, well, as x approaches 3 from the left, it's going down towards negative values. It's going to follow that asymptote down towards negative values. So we would say in this case it's negative infinity. From the right-hand side, as you get closer to 3, your graph is going up towards positive y values very quickly, so we're going to be positive infinity. Next graph looks like this. Same thing. Oops. The limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. Okay, the limit as x approaches 3 from the left, you're going up towards positive values very quickly, so that's going to be positive infinity. From the right-hand side, you're also going to be at positive infinity. Now, because these match, you might argue that the limit exists at this point, but it still does not, because infinity is not a single y value. So it still is not approaching the same y value, because it's going to continue that pattern forever. It's never going to get close to being the same. Okay. For C, and if you're getting the gist here, you might want to find, or pause, find the limits yourself first, and then just use the video to check. Okay. So in this graph, the limit as x approaches 3 from the left is going to be positive infinity. The limit as x approaches 3 from the right is going to be negative infinity. The next graph. Okay, the limit as x approaches 3 from the left in this graph takes you down towards negative infinity. And the limit as x approaches 3 from the right here is also going down towards negative infinity. And again, this still technically does not have a limit because limit is a single y value. Alright, so graphically that's how you would determine limits from a graph, infinite limits. Okay, we're going to look at 2 limits here, I believe. Just double checking, yes. Okay, so we're looking at the limit as x approaches 2 from the right of this function, x squared plus 2x minus 8 over x squared minus 4. Alright, we're going to find all vertical asymptotes here, which is going to be where the bottom is 0. But first we're going to factor and cancel, because if we can factor and cancel, that tells me if I have an asymptote or if I have a hole in the graph. This kind of goes towards along with continuity that we've worked on. So I'm going to factor. When I factor, I get x plus 4, x minus 2 on top, and x plus 2, x minus 2 on the bottom. Okay, so this is what I'm going to graph. So I have a vertical asymptote at x equals negative 2, because if I plugged in negative 2 here, it would give me a 0 on the bottom. I have a hole in the graph at x equals 2. Because if I plugged in 2 originally, I would have gotten an undefined, but because I was able to cancel out, it becomes a hole in the graph instead of an asymptote. Now, to graph what this looks like, you have a horizontal asymptote at 1. I'm just telling you that at this point. And your vertical asymptote that you found at -2. And then if we were to graph this on the graphing calculator, it would look something like this. Now, I think you have to be careful here. The hole in the graph is at 2. So that's actually a hole right there. Okay, so we're going to go ahead and simplify. And actually, I think this is -2. Yes, it should be -2. Alright, now if we're looking at this limit statement, we've done what we can to find the vertical asymptote. I know there's a hole in the graph at 2, but my limit wants to know what's happening as x approaches -2 from the right. So as x approaches -2 from the right, because there's an asymptote at -2, it's going to follow up towards positive infinity. So your answer here would be positive infinity. If you were going to change this question to be the limit as x approaches 2 from the right, here's 2. Well, as you approach 2 from the right, just because we have a hole there doesn't mean that you can't have an answer. And let's actually write that out. Limit as x approaches 2 from the right of your function. Because both sides of the graph, you're going to meet at the same spot there. So we should have a limit. And because we factored and canceled, it ends up working out that now I can directly substitute in. So if I took 2 and I substitute it in here, you get 6/4, or 3/2. So again, this is getting at the idea from limits that when you factor and cancel, a lot of times you can directly substitute. And when you can't cancel, then it's going to be something like -infinity, infinity, or it's going to be a complete break in the graph, which you can label does not exist. Alright. So example 3, determining infinite limits. We're going to look at 3 examples here. A, B, and C. C will get us prepped for the 4 type problems tomorrow, which I think is that's just for my reminder. Okay, so determining infinite limits. We're going to look at limit as x approaches 1 from the left, this function x squared plus 1 over cotangent of pi x. Now, I can't directly substitute because when I do, I get 0 on the bottom. I'm just letting you know that. Right? Cotangent of pi. Yes. Okay. So, direct substitution doesn't work. So I would go to your table, because this is what would be normal for you anyway if you're doing this problem. Cotangent. Cotangent you can put in by doing 1 divided by tangent of pi x. And let me just make sure that my mode is in radians. Whoops. Oh, sorry, I'm using my table. Okay, I just want to pick values to the left of 1. So, direct substitution does not work. So then we use a table. Values to the left of 1 are 0.99, 0.999, 0.9999. Okay, because we care what's happening there. So 0.99, 0.999, 0.9999. Okay. Now, in this case, you keep getting smaller and smaller and smaller and smaller and smaller. So maybe this one is narrowing down. if you have an asymptote, your values aren't going to get smaller and smaller and smaller. They're going to get larger and larger and larger the closer you get to that asymptote. So because we keep getting smaller and smaller and smaller, like if I went to 0.99999, you're going to get closer and closer and closer to the value of 0. So this one actually is 0. You know what? Cotangent of pi is 0, so that makes sense. Let's flip. Right? Yes. I don't know why I put that in as an example actually. Because that'll help me practice infinite limits. But we are also working on limits from the left and the right, so that might be why I included it last year. Okay, so that's my example. And because the table worked out and I saw that it wasn't following an asymptote because the numbers weren't getting larger and larger and larger as you got closer, then I could say with confidence that because this is like negative 0.0622 and then this is even smaller, and this is even smaller, then I'm confident that I'm approaching 0 as my y value. For b, we're going to look at the limit as x approaches 0 from the right of 3 cotangent of x. So 3 times 1 divided by tangent, 1 divided by tangent of just x, right? Go right table. Okay, so for this one, if I'm looking at 0 from the right, that means I'm going to pick values really close to 0, like 0.0001, 0.001, 0.0001. Okay, so now you can see that, hey, my values, my y values, oh, no, you can't see that, sorry. Your y values are decreasing quite rapidly the closer or the further you get away from the values, which means as you're getting closer to 0, your values are increasing by quite a bit. So this kind of pattern indicates to us that we have an asymptote, and since they're going in the positive direction, this is going to be equal to positive infinity. Okay, and I think that's where we're going to stop. We're going to do type 4 problems on Monday together in class, plus looking at problems where you're expected to just think through it instead of using a graph, a table, and an algebraic method, but just different ways that you can use mental math strategies to find the answer. We'll do that on Monday. Have a good weekend.